Okay, let's further our journey into the nervous system, and we're going to look now at muscle contraction and muscle recruitment by discussing the motor unit to begin with at least. So here we have a somatic motor neuron. Now in this instance, if this cell were to synapse with another multipolar neuron, then it would just be a part of the nervous system. But in order to form a motor unit, the motor neuron has to synapse with, he says, there we are, muscle fibers. Now I've just done this as a very basic overview of the process that's going on here. There'll be far more connections and there'll be far more fibers, and obviously muscle fibers don't look like that, but just to give you an idea. By the way, if you're listening to this video before you've started listening to the one on the skeletal muscle system, a muscle fiber is synonymous with muscle cell. It's just because they look fibrous under a microscope, so muscle fiber. You may be familiar with type 1 and type 2 fibers and the variations of type 2 fibers that we have in the body. We're not going to dive into the physiology of that, but it's interesting that a single motor neuron will only synapse with one type of muscle fiber, so be it type 1 or type 2 in this instance, just to keep things simple. However, there's been some interesting research that came out rather recently that has shown that if you take a type 1 muscle fiber, and I'm going a bit off piece a bit here, but type 1 muscle fibers, isolate them, and you attach a motor neuron that was previously synapsed with type 2 fibers and attach them to the type 1 fibers, the type 1s will slowly change into type 2s. This obviously can't happen in the body, but it's interesting if nothing else. So this is essentially what we are measuring when we use our surface electromyography techniques. We are measuring the neuromuscular system, the relationship between the nervous and the muscular system. That's what we're essentially detecting when we're looking at muscle activity and muscle recruitment. So there we are. Now, each muscle will be innervated by motor neurons, and innervation simply means that they're entering the organ of the muscle. A muscle is an organ, it's made up of more than one type of tissue, so it's an organ. So the motor neurons tend to innervate from the side of the muscle, depending on the orientation of the muscle. They won't come in superiorly or posteriorly, they'll come in from the sides, superiorly or inferiorly I should say, they come in from the side. This is an even more simplified version of a series of motor neurons. Now, what we have here, and hopefully you've spotted the difference straight away, is the example on the left has more neurons coming in, this muscle, but each neuron has fewer axonal terminals and therefore is making fewer connections. However, the muscle on the right has fewer motor neurons innervating it, but each of those neurons has far more connections with the muscle fibers. So I would encourage you to pause the video here and consider why that might be, why we have these differences in innervation between these two muscles. And the answer is the muscle on the left is most likely a muscle that is required for endurance-based activities. Now this could be anything from your soleus to the various muscles in your hand that you might use for writing, those that are required for long-term activity that don't require a lot of power, a lot of force generation, but they do require regular recruitment, and they are going to be required to be recruited for a long period of time. Now, the purpose of this is that when the neurons recruit their muscle fibers, when the motor neurons are activated, they won't necessarily all be activated at once. Again, it's a very simple example, but you may just have these four to begin with, and then once they start to fatigue, you'll start to see this one come online, so these two can take a rest. And the idea is that you are trying to minimize fatigue in these muscles, and muscles with a high innervation ratio, so that's a muscle with many motor neurons innervating it, tend to have a greater ratio of type 1 muscle fibers. Now, the muscle on the right here, the one with fewer neurons but making far more connections, may be a large power producing muscle, such as your vastus lateralis, your most lateral of the quadriceps muscles. In this case, we have a muscle that is required to produce a large amount of force over a short amount of time. Let's say we're kicking a ball, for example, we're playing football, kicking a ball. The quadriceps aren't required for propulsion really when running from A to B, so they have, the lateralis has a far higher ratio of type 2 muscle fibers, and therefore fewer neurons entering it. And the purpose of this is simply that when a motor neuron is activated, its action potential propagates down the axon, and all of the cells it synapses with, or fibers, will be activated, or will be engaged. It doesn't just say pass the action potential to just, I don't know, these few here, but leave out these three here. All of them will be engaged. And bearing in mind that motor neuron can synapse with anywhere from 2, I think is the lowest I've ever heard of, up to 10,000 muscle fibers. So in the case of the example on the right, this is where we want to produce a lot of power very quickly. Fatigue isn't so much the factor that we're worried about, we just want a lot of force, a lot of power very quickly, and that is opposed to this muscle here. So this will have a lower innervation ratio, and the muscle on the left will have a higher innervation ratio. So when a muscle is stimulated by the nervous system, it will produce a twitch response, and you can sometimes see this for yourself when and if you do any strenuous physical activity. So for example, if you've gone for a particularly long run, for example, perhaps look at your calf muscles, you will sometimes see, if you just sort of sit down, relax, and then take the time to just cool down, small patches of on the calf muscles just twitching, there's no other word for it, and this is called a twitch response. So this graph shows the amount of time here that's passed, and up the y-axis we have tension. You can think of that as force. Tension is just another way of describing it. So the period up to stimulation, so around about here, would be called the latency period. From here up to about here is the contraction period here, and I'm estimating here roughly, and from this point onwards, so just beyond halfway, if this line is perfectly a perfect bell curve, So roughly from here onwards we would call the relaxation period. That's if we don't experience another twitch contraction anywhere in the muscle, another motor unit isn't engaged, then you will just see this single twitch response. Now if you do see another twitch response, so let's say this little peak here, again we've got the same graph, tension, pretend that's force, time. So this twitch response here, let's say that's this one here, this first peak on this graph, and let's say another motor unit is recruited before we've gone into the full relaxation period, then that will increase the force output here, and then you recruit another motor unit and another until you've recruited as many as you physically can, in which case you produce what is called a Titanic response, as you can see on the graph. It's actually physically impossible to recruit 100% of your motor units and therefore muscle fibers through general everyday activity, for the simple reason that your body always wants to leave something in reserve for in the event of danger. So it's an evolutionary response. You don't ever want to be in a situation where you've recruited all of your muscles, but it is an interesting example into how the potential power that we are able to produce. A friend of mine, this is a little anecdote, so you might want to get a cup of tea and sit down there for this one. A friend of mine in high school, we were in high school science class, biology in fact, and was it biology? No, it can't have been. Anyway, I'll digress. We were doing something with wiring plugs, I can't remember what exactly, and it was a very basic task, and most people can wire a plug, and so he thought it'd be clever to wire two plugs together on a single cord, and he put one in one socket, one in another right next to it, and turned it on. He wanted to turn both of them on, but he only had time to turn the one on the left on. Now I heard a clap of thunder, which was obviously just an electrical explosion, and my friend was on the other side of the room. He, with no exaggeration, was 5 meters away from where he'd been, seated on one of those science stools, if you remember back to high school, those big stools that you used to have to sit on. Or maybe that was just my era. Now, it would be very easy to think, well, he was forced back by the explosion. It generates a force. There's no such force there. There's nothing there. The reason he was able to jump that far back from a seated position is because as he was being electrocuted, he involuntarily recruited all of his skeletal muscles to, at least 100% of their capability, and over such a short period of time, and that generated such a significant amount of force that he propelled himself, he physically jumped from one side of the class to the other. Well, a good distance anyway, something that you could never replicate by simply training to jump that far from a seated position. Now, I'm not recommending electrocuting yourself as part of training, but it does show the potential of the neuromuscular system and of the human body in terms of what we are capable of doing, but also he was extremely exhausted afterwards, and there's a good reason why we don't want to recruit all those muscles all at once. So, the next concept we're going to cover is motor unit recruitment, and this is Henneman's size principle. Henneman's size principle is one of the few things in at least our area of science that I can say with I never want to say 100%, but I would be tempted to say 100% certainty is true. Scientists are notorious for saying, well, it's 99.99% certain, but we won't go to 100. Henneman's size principle cannot be broken. It certainly doesn't appear to be able to. And what do we mean by this? So, Henneman's size principle refers to the order in which muscle fibers are recruited during physical activity, during any exertion you perform. So again, as a basic example here, I have got someone here performing an isometric contraction of their bicep, and I've enlarged to a good degree the individual fibers of the tricep, the bicep rather, sorry, I'm seeing tricep there now. And at this point there's no engagement whatsoever. So we may initially see recruitment from a few type 1 fibers, because again these are the high fatigue but low force producing fibers, and the biceps brachii does have generally a greater ratio of type 1 to type 2 fibers. However, if the activity is prolonged, we may need to recruit all of the type 1 fibers, and only once this has been done can we go on to recruit the type 2 fibers. The type 1 fibers must be fatigued before type 2 muscle fibers can be recruited. You may see in some Muscle and Fitness magazine or something similar, this exercise will help you preferentially recruit type 2 fibers. Utter tosh, I say. You have to fatigue the type 1s first. If, for example, you're performing some resistance exercise and you're doing your 1 repetition max, then the type 1 fibers will be fatigued instantly, almost instantly, and the type 2 fibers will engage straight away. So there's no need to bypass, they'll be exhausted anyway. But again, I've left 2 here. I mean, there's several thousand muscle fibers in your, I think it's about 10, 10,000 I mean, muscle fibers in the biceps brachii, roughly, give or take. But we don't recruit all of them.